What are the odds? The first clear evidence for life elsewhere in the universe discovered via a remote sensing technique right here in our cosmic backyard. Is it really what we think it is? Did we really just find strong evidence for life on an exoplanet in our own planetary system? If so, how and why? And if it isn't what we think it is, then what is it? And why is this discovery such a big deal? It all goes back to a paper published in 2025 in the journal Nature Astronomy. The paper's authors reported the discovery of dimethyl sulfide, or DMS, in the atmosphere of K2-18b, a very hot gas giant around 120 light-years away in the constellation of Cygnus. That's actually pretty close in astronomical terms. The scientists claimed that the amount of DMS they found was at least 20 times higher than the amount we have here on Earth. Now, before we go any further, let me be crystal clear. No one has confirmed this detection yet. No one else has been able to repeat their experiment and verify their results. But even if it turns out that the original researchers were wrong about the amount of DMS, the fact that they were even able to detect it in the first place is incredibly exciting and important. But what is DMS, and why should you care? Well, on Earth, DMS is only produced by living things like phytoplankton in our oceans. It's never been found in the atmospheres of any planets or moons except for Earth. And there's no known geological or biological process that could produce enough DMS to make it an abundant part of the atmosphere of a gas giant like K2-18b, at least none that we know of on Earth. And that means that if there really is DMS in the atmosphere of K2-18b, it must have come from something producing it, something like life. Okay, now that I've got your attention, let's talk about exactly how astronomers think they detected DMS in the first place. It's also relatively young, at least compared to our Sun, at just over 1 billion years old. For comparison, our Sun is almost 4.5 billion years old. Because K2-18 is so much smaller than the Sun, though, it's not nearly as luminous, and its habitable zone where liquid water could exist on a planet's surface is much closer in. In fact, K2-18b lies at the inner edge of that habitable zone. It's an extremely hot gas giant about twice the size of Jupiter and 8 times more massive. It orbits its star once every 6 days at a distance of just over 15 million kilometers. Now, obviously, when we talk about the discovery of DMS, not the hypothetical life that may or may not have produced it, we're talking about the hypothetical life on K2-18b. Here on Earth, the main source of atmospheric DMS is our oceans, which cover about 70% of the planet's surface. When phytoplankton in our oceans photosynthesize, they release DMS into the atmosphere. The reason that phytoplankton do this is still somewhat of a mystery, but scientists think it might be a defense mechanism against being consumed by other organisms. They may also release DMS as a byproduct of normal cell function. Regardless of the reason, Earth's oceans are so vast that phytoplankton produce about 4,000 megatons of DMS each year. And while DMS can and does dissolve in seawater, most of it stays in the atmosphere where it can exist for months at a time and travel thousands of kilometers from its point of origin. So how do you detect a chemical like DMS when it's so far away? You can't just send a little rover over to K2-18b to take a sample of its atmosphere and run it through a spectrometer. You have to get creative, and scientists did. They used a technique called transmission spectroscopy. Basically, astronomers observed the light from K2-18b's star as it passed between us and the star. This occurs during what's known as a transit, which is when the planet passes in front of its star from our perspective here on Earth. As the planet moves in front of the star, some of the light from the star passes through the planet's atmosphere and makes its way to our telescopes. We can then look at the spectrum of that light and see which wavelengths of light were absorbed by which chemicals in the planet's atmosphere. This is how we've been able to learn so much about the atmospheres of planets and the atmospheres of planets outside our solar system. It's also how we were able to detect DMS in the atmosphere of K2-18b. But there's a slight problem. While this technique works great for large planets like Jupiter, Saturn, Neptune, and Uranus, it doesn't work as well for smaller planets like the Earth. See, the larger a planet is, the thicker its atmosphere is. And the thicker a planet's atmosphere is, the more of its light will be absorbed by that planet's atmosphere when it passes in front of its star. On top of that, the larger a planet is, the more massive it is, and thus the stronger its gravitational pull is. And the stronger a planet's gravity is, the faster its atmosphere will move. And the faster a planet's atmosphere moves, the more Doppler shifted the light coming from that planet will be. And knowing the degree to which the light is, Doppler shifted, allows astronomers to determine the speed of the planet's atmosphere. In other words, larger planets have atmospheres that are easier to study because they're thicker, which means more of the light gets absorbed. And they're more massive, which means their atmospheres move faster, which means their light is more Doppler shifted. This isn't too much of a problem for hot Jupiters like K2-18b because their atmospheres are already very thick, and their gravitational pull is strong enough to make their atmospheres move fast enough to be studied with current technology. But it is a problem for planets like the Earth, which have relatively thin atmospheres and weak gravities. Their atmospheres simply don't move fast enough for current telescopes to measure the Doppler shift. So you might be wondering how scientists managed to detect DMS in the atmosphere of K2-18b, which is a hot Jupiter. I mean, they can't detect it in Earth's atmosphere, can they? Well, not directly, no. But they can detect what's called a secondary eclipse. A secondary eclipse happens when the dark side of a planet faces us instead of its illuminated side. This occurs when the planet passes behind its star from our perspective on Earth. During a secondary eclipse, the planet blocks some of the light coming from its star, and we can measure how much light is blocked in order to learn more about the planet. Scientists can use secondary eclipses to study the atmospheres of planets like Earth, which don't have easily detectable primary eclipses, and that's exactly what the team behind the 2025 paper did. They measured the amount of light from K2-18b's star that was blocked during a secondary eclipse and looked at the spectrum of that light. That's how they were able to identify the chemicals present in the planet's atmosphere. And that's how they think they found DMS. Okay, now that we've got the basics down, let's talk about why the discovery of DMS in K2-18b's atmosphere is such a big deal. Remember, DMS on Earth is only produced by living things. And while we can't say for sure that the same is true on K2-18b, it seems highly unlikely that there's anything on that planet that could produce enough DMS to make it a significant part of its atmosphere. I mean, the hypothetical source of the DMS would have to be widespread because DMS is a part of K2-18b's atmosphere. It would also have to be efficient because K2-18b's atmosphere contains at least as much DMS as Earth's oceans do. And it would have to be long-lived because DMS can survive in K2-18b's atmosphere for months at a time. There's simply no known geological or biological process that could meet all three of these criteria. And that means that the most likely explanation for the presence of DMS in K2-18b's atmosphere is that there's life on the planet. Maybe lots of life. This discovery has shocked the scientific community. Most astronomers agree that the discovery of DMS is exciting, but many have said that it's too early to say whether it's evidence for life. There are several other potential sources of DMS that haven't yet been ruled out. For example, there could be a type of phytoplankton on K2-18b that we haven't yet discovered. Or maybe there are volcanoes or hydrothermal vents on the planet that are producing DMS. Still, the most likely explanation remains life. And if that's true, then the discovery of DMS in K2-18b's atmosphere is one of the most important discoveries in the history of astronomy. I mean, it's literally evidence for life elsewhere in the universe. Of course, we won't know for sure until other scientists are able to repeat the experiment and confirm the presence of DMS. But even if the original researchers were wrong about the presence of DMS, the fact that they were able to detect what they thought was DMS in the first place shows us that it is possible to detect what's on planets that are relatively close to us. Maybe not Earth close, but close enough. And that means that we may just be a few years away from discovering the first clear evidence for life elsewhere in the universe. Researchers say that it will be about 4 years until we can observe K2-18b again and check for DMS. And if you ask me, that can't get here fast enough. What about you? Let me know in the comments below. If you enjoyed this video, be sure to subscribe for more videos about space in the future. Thanks for watching, and I'll see you next time.